Thanks for the introduction. Hello, everyone. So I'm going to talk about pattern complexity and two-dimensional shifts. Maybe I can start by saying that I don't have that many slides, so don't hesitate to interrupt me anytime and ask questions, make remarks, tell me if I'm wrong. Well, don't hesitate to interrupt me at any time. So, well, I will start by introducing what are shift spaces. I would guess that most of you already know, but just in case. So I start with taking a finite alphabet that I will call a finite alphabet or colors, and what I will call a configuration is just a coloring of Z2 with this finite alphabet. So here an example. And what is called subshift or just a shift is a set of such configurations, but with an extra condition on this configuration that they should not have any forbidden patterns that appear in them. So for example, here, if I take a forbidden pattern that is just the blue color, then all the configurations of this shift should not have blue in them. I can take another color, or I can also take more complicated patterns. In fact, I can add any pattern in the set F. And here, if I forbid this set of patterns, the only configurations that will be in the subshift will be constituted of lines of purple and lines of green. And if I forbid purple to be to the bottom of green, then the only configurations will be of this type. So with a line separating purple and green. And I will also have in the subshift the all purple and the all green configuration that corresponds to shifting the limit between the two, either to the infinity to the top or to the infinity to the bottom. What I call a shift of finite type is just when the set F is finite. I will talk a lot about periodicity and aperiodicity. And in general, I will try to stick to calling a configuration. I mean, periodicity will designate the configuration, and aperiodicity will always designate a shift. So a configuration that is just periodic or one periodic is a configuration that has a single periodicity vector. So when you translate the configuration on itself, you end up with the same configuration. And the configuration is two periodic. Well, if you have two non-collinear vectors, which is a bit stronger. And I will call a shift, a set X, aperiodic if it contains no one periodic configuration. So none of these configurations will be allowed to be one periodic or simply periodic. We can play and define, well, two definitions of aperiodicity depending on which periodic configuration you look at. But there is a miracle in dimension 2 if you consider a shift of finite type. Then the two possible definitions are actually equivalent, because having a one periodic configuration is equivalent to having a two periodic configuration for a 2D SFT. And for subshifts that are not SFT, if I say they are aperiodic, I mean that they don't have any one periodic configuration, as it's written here. Then the other big definition I need is also very simple. It's just defining the pattern complexity of a configuration. So the pattern complexity is just the number of rectangles of a given size m and n that appear in our configuration. So what you do is just look at your configuration and you slide over all your configuration, a window of size mn, and you count how many different patterns you observe, and that makes the pattern complexity of the configuration. So in dimension one, if instead of a two-dimensional configuration, you consider a one-dimensional configuration, so a coloring of Z instead of Z2. In this case, we have a very strong theorem linking periodicity and complexity, which is that as soon as you have a configuration for which the complexity is lower than n for some n, we call this low complexity, then this configuration is periodic. And actually, I forgot to put here, but this is an equivalence. So you have an exact characterization of what are a periodic configuration depending on their complexity. In dimension 2, which is what interested me, it's more complicated, but it's an open conjecture, which is Nivat's conjecture, that states that basically the same happens. Well, this case is not an equivalence, but all configurations that have low complexity should be periodic. So you don't have equivalence because you can build aperiodic non-periodic configuration that have high complexity. But in that direction, it's still open today. And we believe that that this is true. So I spent a lot of time working on this conjecture. And one of the results I got with Jarkko Kari is that, well, if you look at the subshift, so you take any subshift, you take a configuration in the subshift. And as soon as this configuration has low complexity, then you can find another configuration in the subshift, in the shift X that is periodic. So if Nivat's conjecture is true, of course, C itself is already periodic. Here, what we managed to do is a bit weaker result, where we find another configuration in the shift X that is periodic. And for those who know what is the orbit closure, we can actually find the configuration D in the orbit closure of C. And what is the starting point of what I'm going to present today is actually the opposite of this theorem. So if you take the contrapositive of this theorem, you obtain the following corollary. If you take an aperiodic subshift, so a subshift that has no, well, I decided today that we're going to talk about shifts. So if you take an aperiodic shift, then you know that any configuration of X will have a high complexity. Because, well, if it's not the case, then you have another configuration that is periodic and your shift is not aperiodic. So you have a very strong information on the complexity of the configuration of any aperiodic shift. You know that it should be bigger than mn+1. And well, the starting point is, can we do better than this bound? In general, for some examples, I don't know. It's a property that has not been that much studied in dimension 2. So many questions are still open. But essentially, that's what I'm interested in now, because, well, Nivat's conjecture is maybe too hard. I don't know, but I started thinking, instead of proving Nivat's conjecture, can we improve this bound on aperiodic subshifts? And there are some results that are somehow a bit related, even though they do not really answer this question. I can think of a paper of Julien Cassaigne that proves that exactly characterizes the complexity of configuration that have complexity exactly equals to mn+1 for all mn. And actually, if you look at such configurations, the shifts that they produce, the orbit closure, is not a periodic. You always have a periodic configuration in this shift. On the other way, if you look at trying to find some aperiodic shift or even one periodic configuration with the smallest possible complexity, well, you can find some results about this in a paper from Valérie Berthet and Laurent Vuillon, in which they prove that by taking some two-dimensional projection of a discrete plane, you can build a configuration that has complexity mn plus n for if you're careful with choosing the angles of the plane and how you project it. So that's actually quite close to what we have, the mn plus 1, but still it's not exactly mn plus 1. So we don't really know what's happening between mn plus 1 and mn plus n. And maybe the question that interests me the most is maybe not about general shifts, but more the shifts that represent tilings, or in other words, SFT, shifts of finite type, where we can only forbid a finite set of patterns. And in the direction, I like to understand a very nice result of Emmanuel Jandel and Michael Rao as a kind of starting point from studying the complexity, because they prove that you can build an aperiodic SFTs with Wang tiles, with only Wang tiles, but also that this is the optimal. You cannot do better. So maybe quickly, a Wang tile is just a finite set of tiles with colors on their sides, and then you can match them if the colors are the same. And this kind of tilings are exactly SFTs, can represent exactly all SFTs. And so I like to understand the results as proving that for m equals n equals 1, so a complexity p of 1, 1, the best bound you can have is exactly 11. So you cannot have aperiodic SFTs, or at least with Wang tiles, with less than 11 tiles. But if as soon as you take m and n more general, we don't have better bound than what we have with Yarko. So there are two directions on which to work. We have seen that we have one lower bound, mn plus 1, and we have some kind of upper bounds with some results related to shifts here. So that's one upper bound. But for SFTs, we don't have a general upper bound. And today I'm gonna talk more about lower bounds, and more specifically about substitutive shifts. So why did I go into the direction of substitutive shifts in particular? It's because a lot of aperiodic tilings, as I mentioned earlier, well, not Jandel and Rao, but many aperiodic tilings are built with some kind of substitution ID. So you build some tile set that represent a sort of substitution, and when you take a fixed point of this substitution, you end up with something that cannot be periodic thanks to the substitution. Well, we will see how the substitution works just right now. So substitution, if you look at dimension 1, it's quite easy. You consider a function that takes some letter of the alphabet and that returns a word. And you can naturally extend this substitution to apply it on words instead of simply letters by applying the substitution on any single letter of the word W. From a substitution, we can define what we call a substitutive shift associated with the substitution, which is the set of words that are in which all the patterns are produced by the substitution. And what I mean by that is that for the word to be in the substitutive shift, you need that all the patterns must be of the form sigma to the k of a. So for example, here, if we take the very famous Fibonacci substitution, and we take some pattern P that maybe is a pattern of a word W, then for W to be in this shift, we ask P to appear in a bigger pattern like that, and that this bigger pattern is actually the image of the iteration of the substitution. So here it's sigma 5 of 0. And if this is true for all the patterns of the infinite word W, then the word is in X. The complexity of these one-dimensional substitutions are quite well understood. Maybe the result that sums up pretty well what we know is this theorem by Poncio, which classifies all the possible complexities you can have, all the possible complexities that you can have for the words of the subshift X sigma. So if you take any word of the shift associated with sigma, then the complexity is bounded in big omega in one of these functions. So either it's constant, or it's linear, or in n log log n, or in n log n, or in n square. And the function you choose depends only on the substitution. And if you look in the paper, you can really just, looking at the shape of the substitution, already know what will be the growth of the complexity function of the configuration. Sorry. Now, of course, I'm going to talk about dimension 2, and I'm gonna restrict myself for now to uniform square substitution. So in other words, substitutions that take one letter and then return a square, and all the squares will be of the same size m. So here it's 2 by 2 square. And well, in this case, I can define the substitutive shift, which will be the set of this time two-dimensional configurations for which all the patterns, it's exactly the same definition, all the patterns should come from the iteration of the substitution on a single letter. So if I take some two-dimensional pattern, I ask that I can find it in some bigger pattern like this, that is actually, if I desubstitute it like this, so I take this was an image of just this white color, for example, and I continue to desubstitute it, then in the end I end up with a single letter A. So in the other direction, I substitute certain number of time, and then my pattern appears. And we still know some results about the pattern complexity of such two-dimensional substitution. The finding an upper bound is quite easy, and some people, in the review of my paper, tell it's really easy. It's folklore, everyone knows it. The only place where I actually found a written proof of this is in a book of Robinson, and you can prove that the pattern complexity is actually always smaller than a constant times n square. And well, with our bound with the Arco carry, this also proved that since we have when it's aperiodic, we know it's bigger than n square plus 1. So we proved that it's a big omega of n square in this case. So that's a nice remark. But what is the constant of this n square? Because, well, if the constant is 1, then it doesn't really improve on our n square plus 1 bound. But on the other hand, if we can have a bigger constant, it will prove that substitutive shifts are, well, way above general aperiodic shift. And this is exactly what we tried to prove with Colin Petitjean, who was doing an internship with me. So we proved, I will come on the hypothesis later, but we proved that for some substitutions, we have a bound Cn square with a C strictly bigger than 1. So in this case, we know that the complexity will be really much higher than the Mn plus 1 bound we have with the Arco carry. And to come back on the hypothesis, well, we ask the substitution to be uniform square. So just in the case I described earlier, primitive, which means that all the letters appear if you iterate enough time the substitution, and recognizable and marked. So for these two, I'm gonna define them. So marked substitution are substitutions where a single position allows you to determine the antecedent of the substitution of the image. So on the left here you have a marked substitution, and on the right you have a non-marked substitution. So on the left you can see that if you just look at the cell in red, because you see all the three letters in this single cell on the bottom left, just looking this letter will allow you to know what was the antecedent. On the other hand here, if you look at our full four positions, none of them will allow you to recover the antecedent. You will need to see the whole pattern, or at least maybe not the whole pattern, but more than one single cell to know the antecedent. So marked is when you can do it. Recognizable is a property of being able to desubstitute in a unique way. So what does it mean? It means that as soon as you have a big pattern like this, n times m, which is bigger than some constant here. So as soon as your pattern is big enough, then you can find a unique grid, like the red grid here, which allows you to desubstitute this pattern. And the position of the grid is unique, and you know this position just by looking at the big enough pattern. And why is this property useful in our case? Because this is exactly equivalent to the shift being aperiodic. And the most general case has been proved by Solomiak, even for non-square substitution, or even substitution not at all on the grid. And Solomiak proved that this property of recognizability exactly corresponds to the fact of the shift being aperiodic. So it's really nice for us because we are exactly interested in understanding the complexity of aperiodic substitutions, so recognizable substitutions. So back to the theorem, we have so our substitution that is primitive, recognizable, and marked. And then in this case, we can prove this nice lower bound. So what's the proof ID? It's a very nice, well, very easy proof actually. You in big from far away, let's say you just take your patterns, you desubstitute as much as possible, and then you count how many patterns you have, and you end up with as at most well, at least these many patterns. Well, in details, this is a bit more tricky, of course, but essentially this is what we do. We just desubstitute as much as possible and count the number of patterns. So to desubstitute as much as possible in just one step, instead of considering sigma, the substitution sigma, I will consider sigma to the k, so the k iteration of sigma, with k the biggest possible, such that all n squares are recognizable, so n bigger than rho k, which is the constant associated to sigma k. So I take biggest k possible to have a sigma k n patterns recognizable by sigma k, and I'm gonna desubstitute these n patterns. So I take some patterns of size n, and just to recall, sigma k is now a substitution of size mk times mk. And since by assumption this pattern is recognizable, I can find in a unique way a grid spaced by mk that I can for which I can desubstitute. So this will be this each square will be the image of some letter. I also know that my substitution is marked. So in this grid, I can mark many positions that will, just by looking at this position, allow me to know which is the letter that was substituted to obtain this square, this big square. Well, I will denote A and J the position of the first here I see, but I don't need it right now. What is important to remark is that I actually don't really need to know all the content of this big pattern to desubstitute it. I just need to look at the marked position, since just the marked position will actually define the desubstituted configuration, the configuration from which I obtained my initial pattern. So in order to know how many possible configurations I can have, I just have to, let's say if I call this A and B, I just have to know how many of these marked position I see in a A times B window. And this is exactly this here, this ugly ceiling functions. I exactly see this number, yeah, this number of marked positions. So in other words, for any pattern of size, no, A times B, I can build one pattern of size n, and this for any different I and j. So in other words, I can build an injection between this big set, this big union of many sets, many languages, into the set of patterns of size n. So if I take the cardinal of these two sets, I know that the size, the pattern complexity, which is the size of the language size n, is bigger than the sum of is bigger than this sum. And well, so the thing is that now that I have this sum, this complexity I can have a bound on, because sigma of C is in X sigma. So I know that this configuration sigma of C is aperiodic, is not periodic. So by our bound with carry, we know that the complexity of this configuration is mn plus 1, or here ceilings times ceilings plus 1. And then we just have to compute this sum. And when we do this, we happen to find something in n square. Well, there are other terms, but we don't really care about them. What we care is that this sum is bigger than C times n square, with C a constant that just depends on rho, the size from which sigma is recognizable. So C only depends on sigma and not and not n. And this is, of course, bigger than 1 because it's 1 plus something positive. So we have our result. Of course, somehow this result is not enough because, well, we have many hypotheses, so it seems that it's quite restrictive, and we don't talk about many substitutions in this result. First of all, something that convinced me that it's not that a small result is that any binary substitution which is not constant is actually marked. Maybe I should have prepared the slide on this, but as soon as you have a binary substitution if the images are not all the same, you will necessarily find a marked position. So our results actually, if you look at the binary substitution, you don't need the marked hypothesis. But for more general, of course, it's harder. So let's look at recognizability hypothesis. We really need it for our result to hold, because if you have a non-recognizable substitution, it means that the shift is not aperiodic, so you have periodic configurations. And in this case, of course, the complexity will not be very big in general, and you can have very, very small complexity if your substitution can make periodic configurations. Well, the marked hypothesis is more puzzling for me, because we really need it in our proof, but on the other hand, it seems true without it. So first of all, as I mentioned, if you take a binary substitution, we don't need the marked hypothesis, as all binary would be periodic. All non-constant binary would be periodic. And in general, we made some experiments where we took many random substitutions and looked if they were marked or not, and just computed, well, experimentally their complexity. So we substitute many times. We look at these big configurations and we count the complexity of these big finite patterns, and that gives a bound on the complexity of infinite configurations. And in general, it really seems that marked or non-marked doesn't make a difference on the complexity. You can see here that, well, they are all mixed, the marked and the non-marked, and they are all much bigger than n squared. So it would seem that having a marked, well, a non-marked substitution should not change this bound here. But well, we cannot prove it. And actually our proof really does not work if you use non-marked substitution. And I want to try to explain why with drawings. So if we take the previous drawing and we try to do the same, we take some big n pattern and we try to desubstitute it, but this time with a non-marked substitution. If your substitution is non-marked, you don't have these magical orange marked positions. And well, yeah, so you don't have these marked positions. So the only thing you can really desubstitute, looking at your n patterns, are the big square that you see entirely. So here in this case, just the big 4 in the middle. And if you do the computation just like before with this part that you can desubstitute, you end up with still c times n squared constant, but c is much lower than 1, so it's not useful at all. You don't learn anything about the complexity, because you cannot recover well, as well, the complexity on the red part. And well, actually, one of the motivation of doing this talk was to motivate me and work on this subject and come to this talk with a general proof of the non-marked case, which of course did not work because I still don't have. Well, I worked on it, but I did not manage to find the proof before the talk. So I'm just presenting you the marked case, unfortunately. While looking for the proof, I tried some other stuff, and I discussed, for example, with Sébastien Labbé. And well, he provided me very quickly a counterexample to the non-uniform case. So if the substitution you have is not square, is not, well, a uniform shape at least, then the result does not hold immediately. If you take this Cartesian product of two one-dimensional Fibonacci, you end up with a non-uniform substitution. And this substitution seems to have a n+1 to the square complexity. So here the constant will be exactly 1. So yeah. Yeah, to finish this talk, maybe I can, yeah, I have plenty of time. Yeah, so just I forgot to mention that this part here of the proof, the injection and this ugly set and stuff like that was mostly done by Colline Petitjean doing an internship with me. But after she has done her internship, I actually read in details a paper by Anna Fried on one-dimensional Marx substitutions, in which she does exactly the same. And in the one-dimensional case, she finds actually a bijection between a set that looks like a bit this one, and she computes exactly the complexity of the the size, not just a lower bound. And I believe we can do exactly the same in dimension 2. Just the computation is a bit more tedious. You have some specific case to handle. So we did not try to obtain an equality here, but if you are a bit more careful, like Anna was, you can probably find an exact formula for the complexity here, which we did not do. Okay, so what I wanted to say is that on the other side, we are also interested in the power bound. So trying to build aperiodic shifts with as low complexity as possible. And in particular, trying to do this with an SFT is very challenging. So Jarko and myself, but mostly Jarko, has a result where you can build an SFT with complexity n squared plus f of n for f an as small function as you want, as long as it's not constant. So if I say it's slower, you take any non-constant function, and then just given this function, you can build, if you take n big enough, you can build a set P of patterns that are square patterns of size n by n. And then you know that you can build not too many of these patterns, so just n squared plus f of n times n binary square patterns, such that the subshift in which you allow these patterns, so you will see in all the configuration only these few patterns, and then this shift here is aperiodic. So in other words, you can build an aperiodic subshift with a pretty low complexity. So it's not low complexity, but it's well, pretty low complexity. It's still not as good as the projection of plane by Berthet and Villon, but it's pretty close. And Berthet and Villon's technique does not provide an SFT. Here you really have an SFT. And this result come from this theorem here, which basically takes any set of Wang tiles and re-encodes the Wang tiles in a way that produce the SFT we want. So in other words, if you take any set of Wang tiles, you can build a subshift, even an SFT that encodes these Wang tiles in a sort of big n times n squares that represent one tile. And when you do this, you can be careful and produce not too many allowed patterns and build an SFT with these allowed patterns that behaves exactly like the tiling by the Wang tiles T. So in other words, the SFT will be non-empty if and only if the set tiles the plane, and also it will be aperiodic if and only the set T tiles the plane non-periodically. And we do this by re-encoding the tile set into an SFT of pretty low complexity, and by being careful on how we do this encoding. So what to do next? Well, many things. First, I really want to look at the lower bound for primitive aperiodic substitutions, so without the marked assumption. And this should be possible, but everything I tried for now did not work. I always end up with a constant lower than 1. But I still have some hope. Then it will be very interesting to get a general lower bound for general SFTs. So my motivation to look into substitution is because a lot of aperiodic SFTs are built from substitutions. But it will be very nice to have general bounds on SFTs and not just the one that looks like substitutions. And then it will be very nice to maybe improve this lower bound here, this one in particular, because this bound of n squared plus f of n is based on a generic re-encoding setting. So here we can really re-encode any set of functiles in this pretty low complexity manner. So maybe if instead of recoding any set of functile, we take a particular well-chosen aperiodic set of functile, for this particular type, we can be very clever and find a very clever encoding that have a better bound than this, maybe lower, I don't know. That would be very interesting to really be more clever in the encoding by using a particular set of functile instead of re-encoding any general set of functile. And yeah, so that's all I have. Thank you very much for your attention. I hope I did not lose you in the way, and don't hesitate to ask questions.
Oh, thank you very much. Does anyone have any questions for Etienne?
I saw Emily open her webcam, but I don't see her.
All right. If no one has, oh, there is a question. There is a question in the chat. Can you see it?
Yeah. Had you considered block substitution? Not necessarily squares. So yes, we did look a bit into. So I guess you ask still about rectangular case, since we are on a grid. So for example, a substitution like this. So the non-uniform case we saw is hopeless, but the uniform case, and well, I did not tell it here because it's a bit more technical, but we can find a similar bound if the shape of the substitution is pretty close to the shape we look at the complexity. So if this is the rectangle, we look at the complexity, small m and small n, and the substitution is big M and big N. If this has almost the same shape, then we can have the same bound in the marked case. But unfortunately, if the two shapes are very different, then we have counterexamples, and you can imagine that if it's pretty easy to see that it will not really go well if you have a substitution that is a fat square like this, and you look at complexity of really thin stripe like this, then you can build substitution that don't have very high complexity. As soon as the substitution have a shape that is very different from the window you look the complexity at. So yeah, we can have the same result, and we have a bound on what does it mean to be almost the same. Yeah, we have similar bound in this case. Thank you very much for this question.